Today we're going to be exploring the topic of rational expressions and functions from the very beginning of what this topic means in the course of Algebra 2. So specifically, we're going to be looking at the graph of the parent function y equals 1 over x, which is, again, the rational function in its parent function form. And the main details to notice in this diagram is that the rational function 1 over x has both a vertical and a horizontal asymptote, and today we're only going to be looking at the key features of a rational function that you would be able to observe on a graph. So let's go ahead and jump into some of those key features. Hopefully we are already somewhat familiar with an asymptote. So a vertical asymptote is always going to have the equation x equals, and then whatever number the asymptote is passing through is what you would write on the line to show what that equation is equal to. So if you take a look at the example down below, we have a vertical asymptote at x equals 0, and you're going to notice that the green dotted line, which represents the asymptote, is passing through the x value of 0 on the x-axis. So that means the equation would be x equals 0, and in general, whatever part of the x-axis you have your vertical asymptote passing through, perhaps it's going through the number 4, then you would just say x equals whatever that number is. You want to think of a vertical asymptote is like a wall that the function is never going to pass through, but it's always going to approach it forever. So you can see right here with the function, it is getting closer and closer to the asymptote, and then it's going to go up to infinity, but it will never touch the green line. And likewise, the other part of the rational function is going to go down forever, but get forever close to the asymptote. Now, in order to find the vertical asymptote from an equation, we're going to have to determine what x values make the denominator become 0. And we're going to use the skill of factoring that I'm assuming you are already somewhat familiar with. The basic idea is that the denominator of any fraction is not allowed to be equal to 0. So if you saw something like 4 over 0, hopefully your pre-algebra skills would tell you that you're just not allowed to have that type of fraction. So basically, whatever values after we factor the denominator would make the denominator become 0, well, that's going to tell us what our vertical asymptote or asymptotes are going to be. So the main idea to take away from this is that we are going to factor the expression you have right there in the denominator, and we're just going to solve for the x values that make it equal to 0. So let's just start doing that right now, and then I think you'll understand the general idea. We're going to factor x squared plus 2x minus 8, and you would begin by asking yourself the question, what two numbers multiply to make negative 8 and add to make positive 2? And that would be negative 2 and 4. So we can then rewrite the denominator as x minus 2 and x plus 4. Again, I am assuming you are already generally familiar with the skill of factoring, so we are just going to move on through the problem. Now that denominator, now that it says x minus 2 and x plus 4, we are now allowed to use the zero product property. So according to the zero product property, you would take, for instance, x minus 2 and set it equal to 0, and then you would add 2 to both sides and get your first solution, in this case, your first vertical asymptote at x equals 2. And then you would take x plus 4, set that equal to 0, and after subtracting 4 from both sides, you would get x equals negative 4. So what that means is this function, if you were to graph it with a graphing tool like Desmos, it would have a vertical asymptote at x equals 2, and it would also have one at x equals negative 4. So as a quick little diagram of what that would sort of look like, 2 would be approximately right there, negative 4 would be approximately right there, and the function would have some behavior where maybe it's coming from this side and going down, and perhaps it's maybe going down like that, and then maybe over here something quadratic is happening. Probably should have looked this up just to know the diagram, what the diagram would look like, but again, the main idea is that this graph is going to have two asymptotes. One of them would be at x equals 2, and the other one would be x equals negative 4. What you're going to notice at the bottom of the screen is the furthering idea that you will eventually have to incorporate to this type of problem, and that would be finding the domain. The domain is, of course, all of the x values that you are allowed or not allowed to use in your function. And since we have vertical asymptotes, that means you are not allowed to include the numbers 2 and -4 in your domain. So you would just write down what you can see here at the bottom, and the fancier way of writing it with interval notation is also here at the bottom right. You will notice the U for union symbol is being used, and you're going to notice your intervals here, but again, this video is not about interval notation. It is about the key features of these types of graphs. So let's just go ahead and move on to our next key feature. We have the horizontal asymptote. So that is always going to have the equation y equals, and then whatever number the asymptote is passing through. So again, in the example below, you can see that the asymptote is passing through a y value of 0 this time. So therefore, the equation would be y equals 0 for that asymptote. And just like from before, if let's say you had an asymptote that were up here at the number 3, then you would have y equals 3 as the value for that asymptote. Vertical asymptotes will only have x equals. Horizontal asymptotes will say y equals. And you can think of a horizontal asymptote as like a ceiling or a floor that the graph will never pass through or reach. And you can see that right here as we move more to the right. This graph is going to kind of hit the floor, but it will never touch that green line. And then over here, the graph is never going to reach, in this case, the ceiling, being that asymptote. Now, to find your horizontal asymptote from an equation, it is not as quick as the vertical asymptote. There are a few things you're going to have to look at. The initial thing is you got to look at the degree, which from Algebra 1 is referring to the highest exponent, and you have to look at both the numerator and the denominator to make that determination. Now, if your degree, and by the way, as it says at the top, there are 3 rules that are about to be explained, and this is the first of the 3 rules. If the degree of your numerator and denominator are equal, so in this case, you're going to see that you have both the number 2 as the highest exponent in the numerator and the denominator. You have to compare the 2 exponents. And since 2 is the same degree, you are going to just divide the leading coefficients, and that answer is your horizontal asymptote. So you will notice that, again, I'll just have that animation play through. We have the number 2 and then the number 1 as our leading coefficients. So you would simply divide 2 by 1, and that would give you your horizontal asymptote at y equals 2. There'll be some practice problems at the end to review this skill, but that is the basic idea. Once again, the first of the 3 horizontal asymptote rules is that you will examine the degrees. If the degrees are equal, you will just divide the leading coefficients of both the numerator and denominator, and that answer, in this case 2, is going to be your horizontal asymptote at y equals 2. The next of the 3 rules is called, the situation you're going to look for is your function bottom heavy? So in this case, you're going to notice the degree of the denominator is bigger than the degree of the numerator. We have a 2 in the denominator, and that is bigger than the degree of 1. If your function is bottom heavy, then this is actually the easiest part of the horizontal asymptote rules. You are always going to have y equaling 0 as your horizontal asymptote. It is the most convenient one. The moment you notice your function is bottom heavy, then you know your horizontal asymptote is going to be y equals 0. And the basic reason for that, without taking too much extra time, just notice since you're squaring in the denominator and you're only raising a value to the first power in the numerator, the denominator is going to increase way faster as you keep plugging in bigger and bigger x values. So, for example, if you were to put 1 over a million into a calculator, then you're going to see the answer of 0.00001. And if you continued this trend, the bigger the number you're plugging in is getting squared, so that denominator is going to grow way faster than the numerator. You're eventually going to have basically 1 over and then an infinite amount of zeros, which is going to make this decimal infinitely have a 1 at the end with an infinite amount of zeros. So you're never going to quite reach 0, but it's going to approach 0. And that's why the asymptote is at y equals 0. But again, if you didn't understand all of that, then the basic idea is just if the graph is bottom heavy, or the equation is bottom heavy, then your horizontal asymptote is always y equals 0. Now, the third rule, you have to do a little bit of extra work if you are in this situation. So this is called a top-heavy situation with your rational function, and instead of having a horizontal asymptote, you're actually going to have what is called an oblique or a slant asymptote. The word oblique just means it's slant as well. It's not vertical or horizontal. It's oblique or slant. So that means the asymptote is going to be moving at a diagonal. Now, this is only going to happen if the degree of the numerator is just one more bigger than the degree of the denominator. So take a look at the example over here. The degree of the numerator is a 2, and the degree of the denominator is a 1. They are 1 apart, and the numerator is top heavy. So if this situation is happening, and it's pretty quick to recognize, and again, there will be some practice problems at the end. If this situation happens, you actually have to do a skill that I am assuming you are familiar with, and that is synthetic division, or if you would rather use long division, it would also work. You will basically do these skills and then ignore the remainder that you get at the end. So this video is about rational functions. It's not about a strict review of these two skills. So if you need to refer to some other video or some other assistance in order to understand synthetic and long division, then that is something you will need to do. Take your numerator. So you're going to notice 1, -5, and 4. That's where the 1, -5, and 4 come from in synthetic division. You're going to notice a positive 3 is in that spot. Your denominator said x minus 3. So the solution, you always take the opposite number. That would be 3, and that is why you see a 3 written there at the start of synthetic division. So you would drop the 1, do 3 times 1. You would then do -5 plus 3. You would multiply and add, and you would get -2 as your remainder, but you would just cancel that out. And what your answer here means is that x minus 2 is going to be the value of your slant asymptote. The position right here, your first position, is going to be your x value, your x to the first power, and then that second position is going to be your constant term. And this happens because you started your synthetic division with a quadratic. So after you do it once, your quadratic is now going to be a linear function, so an x to the first power. Nevertheless, this skill is something that you may or may not have to review, and if you did it with long division, if that is something that makes a little more sense, here's a quick run through of what that would look like, and you can see that you get the same answer of x minus 2 in your result for long division. So that would be the value of your oblique or slant asymptote. And if this graph were to be drawn, again, I didn't prepare the actual visual of this graph, but x minus 2 would happen approximately right there, so that would be the slant asymptote. So the graph would probably come at it and bounce off like that and probably come up and curve that way. Again, you could put this into Desmos and see exactly what it looks like. Now, the last situation that you actually have to watch out for, this doesn't have to do with vertical and horizontal asymptotes. This is the last key feature we're going to talk about today. When you are able to simplify, you need to. And if a binomial is canceled out, then that means you're actually not getting an asymptote at that location. You're actually getting what is called a removable discontinuity. So that is a higher level vocabulary word. Let's actually move through the math quickly so you can see what I'm talking about. Start by noticing your numerator. It is top heavy. You might want to start by doing synthetic or long division, but you always need to simplify if you can simplify to see if you're going to have a removable discontinuity. That's a very important point that I'm glad I remembered to say. Perhaps pause and rewind that last point again. We're going to take that numerator, we're going to factor it. You can see you get x minus 4 and x minus 5. So this is what the new expression would look like. And now observe that we have an x minus 5 in both the numerator and the denominator. You are allowed to cancel those out. And that would give you the result of x minus 4. So we don't have something that is a rational function anymore. We now have a linear function, which you might now think, okay, I am done. But this is where the removable discontinuity concept comes in. So because you canceled out x minus 5, you will never be able to plug in the solution of positive 5. Because remember, from the zero product property, you would set x minus 5 equal to 0. You would add 5 to both sides, and you would get a solution of positive 5. But because you are simplifying this expression and you canceled out those x minus 5s, you have removed, that's where the word removable comes from, you have removed the asymptote or discontinuity that would have been there because it simplified. So that means positive 5 can never be plugged in ever in this problem. So the basic idea is if you cancel out binomials, whatever the opposite number is, that's going to be your removable discontinuity. So that's why it says x equals 5. I'll say that once again. The basic idea, if you cancel out your binomials, whatever the opposite number is, this says negative 5, so the opposite of negative 5 is positive 5. That number is your removable discontinuity. But let me just erase some of these stray marks really quickly. There is one more thing to notice, and then we'll do a little bit of practice. Your range. Your range is not equal to 1. Where did that 1 come from? You have to, at the very end, you have to take your removable discontinuity value, in this case 5, and you have to plug it in to what the final function became so that you know on the graph where you would visually put your removable discontinuity. So let me just show you that with a little diagram. If you were to graph x minus 4, then you would see this orange line. But because the removable discontinuity that happened at 5, and if you were to plug in the number 5, then 5 minus 4, that would give you 1. That means the removable discontinuity appears as a hole on the graph. If you were to put this original function into a graphing tool like Desmos, and you were to put your mouse over 5, 1, then it would show you that there is a hole in that place. And this is the procedure you always have to do. Consider pausing and rewinding if you need to see this again. I will give you a very quick overview. You always simplify to start things off if you are able to, and if you happen to have factors you can cancel out, then you're going to have a removable discontinuity. You have to then take that removable discontinuity value, plug it back into the function to know what range value you are not able to have in your final answer. And then visually it would look like an open circle. So there are a lot of concepts that were talked about just now that I am assuming you are somewhat familiar with. So whether or not that is true, go ahead. Try some practice problems. Notice how in numbers 1 and 2, I'm just asking you to determine the asymptote. Check if you're going to have a vertical, horizontal, or oblique asymptote. Nothing's going to cancel out. You're not going to have any removable discontinuities. You're just going to make sure you understand the basic idea of finding those asymptotes. And then down here in number 3, you'll need to do a little bit of factoring and see where you can go from there. So on that note, go ahead and pause the video, and I will show the answers to this practice set in just a moment. Okay, and here we go. There are all the answers. Go ahead and take a look at this. Drop a comment if you have any questions, and thank you very much for watching this video. I will see you next time.